Hello, in this session we are going to talk about arctangent primitives. The main objectives for this lesson are to know the technique associated with arctangent type integrals and to apply this technique to obtain primitives. The requirements we will need before we get started are the pseudo-immediate arctangent primitive and the square completion technique. The arctangent primitives are those we have here. Essentially, it is the integral of a fraction with a constant in the numerator and a second-degree polynomial in the denominator, which is irreducible. In other words, it has no real roots. As you may know, this is equivalent to the condition that the discriminant is negative, as shown in square brackets, b squared minus 4a multiplied by c is negative. In this case, we ensure that this polynomial has no real roots. And in this case, the integral that we will obtain has a standard process called the arctangent type. Said process basically follows three different phases. The first phase is to complete squares in the denominator. In other words, to simplify the polynomial in the denominator using the square completion technique. The second phase is to find the 1. We will see what this means as the lesson progresses. And finally, the last phase consists in final adjustments, a couple of little tweaks here and there to make sure that it all works well. And let's begin with an example. We'll take this integral, this primitive, and perform the calculation. As we can see, it fits the form mentioned above. To ensure that it cannot be factored further, we calculate the discriminant b squared minus 4a times c, which equals 4 minus 8, resulting in a negative value. In this case, we are dealing with the arctangent type, and we can proceed with the methodology. Once we have our primitive, let's begin with the mentioned process. The first step is completing squares in the denominator. We write the integral as is, and we leave the denominator, and all we do is take the polynomial of degree 2 and apply the square completion. I do want to believe now that whoever is watching the video knows how to execute this phase without problems, so let's continue on to the next one. Once we have completed the square below, we move on to the second phase, which is to find the unity. And finding the unity means... Let's start the phase. And finding the unity basically means taking the 1 divided by 2 that we have here in the denominator and turning it into a 1. That's the main objective of this second phase. As you can see, we rewrite the integral the same, the numerator leaves it as is, and I only modify the denominator. What I'm going to do now is that, since I need for there to be a 1, and what I currently have is 1 divided by 2, I'm going to multiply the fraction above and below by what I'm missing. In this case, I multiply by 2. By multiplying up and down by 2, I will end up having 2 multiplied by 5 above and 1 below. Let's note that we also must multiply the first factor. That's the reason I had 2 times the parenthesis, and now I have 4 times the parenthesis. With this, we have finished the second phase, the phase that consists in finding the 1. Once we have arrived here, we only have to make some small adjustments. The main adjustment will be to incorporate the 4, which is the coefficient multiplying the degree 2 polynomial, by placing it within the quadratic term. In other words, this entails placing it inside the parentheses. How do we do that? Well, as you know, to enter inside a parenthesis that happens to be squared, the 4 has to enter as a square root. In other words, the square root of that little number. In this case, the square root of 4. And once we have this square root of 4, we can finally simplify. We simplify inside the parentheses. The root of 4 comes as a value of 2, and we do the math. As you can see, the numerator hasn't changed. The denominator has only changed what was inside the parentheses. Once we get here, we could continue making adjustments, but to make the final adjustments, we need to remember the function, the arctangent primitive, which is the one that just appeared in highlighted with blue. A function, an expression of the form function of x squared plus 1 in the denominator and above the derivative, has as its primitive directly the same arctangent of the function. Well, if we look at the primitive that we have right now, we have exactly that form. Below, I have a function squared, which is 2x plus 1, and then I have plus 1, which is why it's important to find the 1. And for it to be an arctangent, we need for the derivative to be above. The derivative of the function that is highlighted with red is 2, so above, I only need the 2. What happens there? Well, I have a 2 and a 5, then I simply take the 5 out. Let's remember that I can take the 5 out thanks to the linearity of the integral. And once we have reached this point, I can directly apply the formula. The 5 is factored out, and on the other side, what we have is the arctangent of 2x plus 1 plus a constant. Why the arctangent of 2x plus 1? Well, because we place the function f in question, in the argument of the arctangent. Well, students, that is pretty much all. What can we accomplish after today's session? We should be able to compute the antiderivatives of functions in this specific way, particularly when the denominator is not factorable over the real numbers. Thank you very much for listening. See you all in the next lesson. Thank you.